Hello friends, so in this video I will talk about why Electron Ion Collider experiment. So this is the scanning electron microscope. Here we basically use the electron gun to generate the electrons, and then we accelerate these electrons and also collimate them, and then these electrons interact with the material, and then after the interaction there are several process by which these electrons interact with the material, and we detect a secondary electron using the secondary electron detector inside the detector, and this detector is allows to reconstruct the surface image of the material. So in this case, this is the surface image of the diamond. This is from my thesis during my PhD. So you can clearly see the grains of the diamond film, and then it allows you to reach typically the resolution of the nanometer level, because it is the electron energy is typically 0.2 keV to 40 keV, and if you use the de Broglie's wavelength, it has the typically wavelength of the nanometer level. Now if you want to image the proton or a nucleon, then basically what you have to do, you have to further increase this energy. So basically you have to accelerate electrons to very high energy. There we require electron accelerators very high with a very large radius, so that we accelerate the electrons at a very high energy, and that will allows you to image the inside the proton. So high energy physics experiments. So we have the LHC, Large Hadron Collider experiment at CERN, Switzerland, and this is the LHC ring, so Large Hadron Collider ring. So we have the 4 collision points here, where we have the 4 major experiments like ALICE. I work with the ALICE experiment, a Large Ion Collider experiment at LHC, and also ATLAS experiment, another collision points where you have again the detectors, and then LHCb experiment, and we also have the CMS, compact muon solenoid. So in this ring we basically accelerate the proton, and then we collide this proton at 4 major points, and also p-lead, proton lead, and the nucleus collisions to study heavy ion physics. So it allows to also study the cold and hot nuclear metal effects, and then the heavy quarks are the ideal probe, charm and beauty. I use them to study the property of the quark-gluon plasma. Now come to the EIC experiment. This is at the Brookhaven National Laboratory, USA. It is a future facility. Here we have the electron ring, again the similar, and then we also have the proton ring and the light ion ring. So here we have the 2 proposed collision points, one at which EPIC is located. EPIC stands for the Electron Proton Ion Collider experiment, and this is overall is known as the EIC complex. Like here we have the LHC complex, and there are 2 collision points, proposed collision points. At one collision points we have the EPIC, Electron Proton Ion Collider, and there's also a proposed collision point on which second detector will be located. This is proposed second detector configuration for this collision point. So here we will use the polarized electrons and proton beam, and also the collisions of the polarized electrons with the polarized light ions. And the electrons, why we are using, it's a point particle, and it allows to have a high precision, and ions, because to probe their structure we want to image what is inside a nucleon, and also the collider, we want to achieve a large center of mass energy. And EPIC has this experiment has a very several important physics goals, and one of the most important goal is the 3D imaging of a nucleon. Now the physics goals of the EPIC experiment. So how are the C quarks and gluons distributed inside the nucleon, both in position and the momentum space? So basically we want to do the 3D imaging of a nucleon, basically 3D imaging of a proton, both in position and the momentum space, and it will allow us to understand how the properties, spin and mass of a nucleon emerge from these the fundamental constituents like quark and gluons and their interactions. And we also want to study the what happens to the hadronic matters to at a very extremely high gluon density regime or a low X regime. So what happens, we have three quarks here and the gluons, and then when you go in the low X regime, your quark, when it is when you increase the energy, it again emits the gluon, and then gluon can again create the two quarks. These kind of things basically increases the gluon and the quark density at a low X regime. Now the question comes whether it saturates at some low X regime or some we have a saturation scale. For this, what we should have the gluon emulsion should be equal to the gluon recombination. So we want to study this whether this saturates with at some energy at a saturation scale. So does this saturation also give rise to a gluonic matter with the universal properties in all the nuclei or even in the proton? And we also want to study how the dense nuclear environment affects the distribution of the quarks and gluons and their interaction in the nuclei. So what we will do, we will study the electron and proton collisions, and we will study the jets, how they behave, and we will also do the electron and the light ion collisions and the electron gold collision, and there you have a more dense nuclear environment. And then we will study again the jet properties that will allow us to understand the energy loss and the hadronization. And so here we will compare basically EP collision, electron proton collisions, to electron nuclei collisions. And it basically also allows us to understand how a fast moving color charge is affected by the dense nuclear environment, and how do the quark and gluons interactions basically creates the nuclear binding, basically hadronization process. So this is all. Thank you.